Hi class, in this video we're going to go over example 1. And here's the basic idea. We're assuming that you have a sample that comes from a population and then a second sample that comes from a second population. And where we're checking is to see if there's a difference between the measurements from the first population and the second population. So let me just quickly talk about what we're talking about in this section. And we're assuming that we have dependent samples. So we would have an n amount of data that was collected, and then it's paired as a first measurement, and then technically as a second measurement. These are not supposed to be in any other order, meaning if the first measurement is collected for one subject, the second measurement is going to be selected from the second subject. So you're not allowed to modify these in any order. It looks very similar to the regression, but it's slightly different. So you're checking to see if, based on the first observation, something happened in between, and then see if after the second observation, if there was a change from the first measurement, but as a whole group. So once again, dependent samples means that you keep track of the first measurement, kind of like a pre-test, post-test, and then see if there's a difference between the first measurement and the second measurement, but for the populations. Now, the notation's a little bit different. So the good news is that everything translates to a actual t-test when sigma's not known. So when they're looking at dependent samples, they're going to be looking at, this is the x bar value, and that would be the standard deviation. They can either call it SD or S bar. Your test statistic, it's just a regular t, except that you're looking at the difference between both of the measurements. And then by hypothesis, you're assuming that mu of d is equal to 0. So in essence, it's the same formula for a t interval and t-test. So that would be your t interval, that's your t-test. Now, let me quickly go over what we actually have. So give me a minute so I can zoom in. Now, for the hypotheses on dependent samples, they're always going to talk about if there's a difference. So your claim, you can always just rewrite exactly as it's stated. In this case, what they really mean is that the main difference between the first sample and the second measurement, it's not equal to 0. Now, what's going to be identical is going to be your hypotheses. And then you're assuming that, well, the first sample comes from some population 1, second sample comes from a second population 2. And then your critical values are going to be all t values. But they're using n, the total number of samples. So in this case, the pairs actually, I mean. So 1, 2, 3, 4, 5. So 5 pairs, and that's going to give us a total of 4 degrees of freedom. Now, for all the formulas on dependent samples, we technically have t values. And the problems may just say they're dependent, meaning the first measurement, meaning that these probably come from the same subject. So same subject, same subject throughout, and they took a measurement 1 and a second measurement. Now, if the c value is not stated, automatically you're going to do 95. And in this case, I'm running StatCrunch with 4 degrees of freedom since our values of n is equal to 5. And then your critical values, or the edges, are going to be plus or minus 2.78. Now, your test statistic. Your test statistic needs a little bit of work. So technically, this would be your L1. You would actually enter the data into L1. Then you're going to enter the second data set as L2. And then what you're going to do on L3 is you're going to do the measurement of L1 minus the values of L2. And all of these are set up in the same form. You end up subtracting these two, and then the one variable statistics, I'm running it here. It's giving me the following for L3. So you evaluate the subtraction, and then you have to do the following adjustment. So everything's done on L3. And once you actually carry out the L1 minus the L2, you're gonna actually say that the mean of the sample, and for dependent samples, that's the bar. In this case, we're getting negative 72.2. The standard deviation, I'm just using the notation of the author. your regular standard deviation of a sample for dependent samples, it's going to be approximately 9.31. Now, your test statistic, I'm just evaluating it here by hypothesis. Mu of d happens to be 0. So evaluating the quantities here, we're getting -17. And that means that as you compare it to the critical value, you're out here on the rejection region. So here I have the final conclusion. In this case, we end up rejecting HO. The test statistic is less than the critical value. So we have sufficient evidence to conclude that the main difference is not equal to 0. In this case, our hypothesis was that mu of d is equal to 0, meaning there's no difference between the pressure on both of the arms, and then mu of d is not equal to 0. So rejecting mu of d, that means that mu of d is correct. There is a difference. Possible placement of the heart, or maybe the actual subjects are taking a medication. But in this case, we have sufficient evidence that they're not, so the mean measurement for the populations are not the same. So the only trick on this one is that everything's actually on L3, which happens to be the difference. So I do want to see on the paper exam, at least the variables that you're using. For the actual critical values, you would be doing inverse T. So in this case, that would be in your calculator an inverse T. So your actual code, I'll just place it here. So your code should be an inverse T and then 0.025 with 4 degrees of freedom. I didn't add it here because the calculator that I'm using on this computer doesn't have the inverse calculator. Okay, lastly, you're also doing shortcuts if they don't want critical values. In this case, I'm just displaying what I'm using for the actual confidence interval. They only want the actual confidence interval for mu of d. This is your formula, your standard error. It's the same as if it was a regular confidence intervals when sigma is not known. But the only difference that you're going to see here is that when you run a t interval, and this is going to be a t interval on your L3. So t interval but on L3, and you're gonna get negative values on some of these answers. Now that's because they're actually saying on average how large do you expect these differences to be, meaning for the population the first measurement minus the second measurement, and in this case the largest this can be is from negative 83.76 to negative 60.64. Also, the software may be asking you to put these as positive values. So if they're asking how large could the difference be between, let me go back to, in this case, the right arm and the left arm. And in that case, the largest of the difference is anywhere between 60.64 to 83.76. Now, it is perfectly fine in this section to express them as negatives. And that is because you're looking at a difference. And when you're subtracting values, that's where your negatives could come up. So on paper, both of these sentences are fine. The software is going to be a little bit picky. If they're asking for absolute value, then that will be your answer. On paper, the negatives will be fine because once again, you're looking at differences. That's actually it for this problem.